My name is Sarah, and I'm a volunteer with Let's Talk Science at the University of Victoria.
Today, we're going to be talking about density and how density drives something called thermohaline circulation in the world's oceans. Some of you might have heard the classic question, which is heavier, a pound of feathers or a pound of bricks? Pause the video and see if you can take a minute to answer the question. Of course, a pound of feathers and a pound of bricks weigh exactly the same amount, a pound. The difference is that you would have to collect a lot more feathers to get a pound of each one. The automatic instinct to say that a pound of bricks is heavier than a pound of feathers is because bricks are far more dense than feathers. This means that feathers have less mass in the same volume than a brick. Mass is the amount of matter you have, while volume is the amount of space that matter takes up. Density depends directly on both the mass and the volume of the object, and the density of something is equal to its mass divided by its volume. So in the feathers and bricks example, you would need a much larger volume of feathers to get the same mass as a smaller volume of bricks, because bricks are so much more dense than feathers. Now that we know what density is, I'm going to do a fun activity that demonstrates the different densities of some common household liquids, and I hope that you'll either follow along with me or try it once you've watched the whole video. Some liquids that are less dense will float on top of liquids with a higher density, and we can use this property to make a cool-looking density tower. This could also be used to test the relative densities of different liquids if you wanted to find out if one liquid was more or less dense than another.
For this activity, you will need a tall, skinny glass, olive oil, rubbing alcohol, corn syrup, water, dish soap, and food coloring.
Now before we get started, I want you to pause the video and see if you can make a guess about how dense these different liquids will be compared to each other. What do you think will happen to the liquids when we mix them all together?
Now that you've hopefully taken a moment to make a guess, let's see what happens when we mix our liquids together. When adding the liquids, make sure you pour them slowly down the side of the glass so they don't mix too much when they land at the bottom. You only need to pour in enough of each liquid so that you can see it make a clear and distinct layer. First, add the corn syrup. Next, pour in some dish soap. Before adding the water, put a few drops of food coloring in it so that you can tell it apart from the dish soap. I'm going to use blue, but any color will work. Slowly add the water. Next, add the olive oil. Like with the water, add some food coloring to the rubbing alcohol before pouring it in so that you can tell it apart from the other clear liquids. I'm going to use red. So according to our density tower, we can see that corn syrup was our most dense liquid, this is why it sunk to the bottom, followed by dish soap, water, oil, and finally rubbing alcohol. How close was this to your guess? If you want to, you can try mixing it all up with a chopstick and see how well the different liquids settle back out. Mine settled out almost completely after about 10 minutes, though the layers with the food coloring were a bit more mixed than when I first added them. When you are finished with your density tower, you can dispose of it safely by pouring it down the sink with plenty of water.
Now that we know that different liquids have different densities, do you think that one single liquid could have different densities depending on other factors? In this next activity, we will explore the relative density of water at different temperatures and at different salinities.
For this activity, you'll need water, ice cubes, a kettle, 2 glass cups or jars, table salt, 2 different colors of food coloring, and a spoon.
First, let's find out how the temperature of water affects its density. Like before, see if you can make a prediction about what you think will happen when we mix cold and hot water together.
To make the ice water, fill 1 glass with water and add some ice cubes. This experiment is a bit trickier than the last one, so we recommend making some extra ice water in case you want to try it a few times. Let the glass sit for about 15 minutes until all the ice cubes have mostly melted. You can also do this process in a measuring cup so that it's easier to pour later. When the ice has mostly melted, pour a bit of the ice water into 1 glass, spooning out any ice cubes that get in. Dye the cold water with food coloring. Fill the other cup with hot water from the kettle, being careful not to burn yourself. Dye the hot water a different color than the cold. I found that yellow and red works the best, but feel free to try different colors. Very slowly, pour the hot water into the cold water, making sure to pour it gently down the side of the glass until all the water is in one glass. If you have any spilling, make sure to wipe it up quickly so the food coloring doesn't stain your counter. Though it's not quite as obvious as the density tower with different liquids, we can see that the hot water is less dense than the cold water, and so it floats on top.
When water is heated up, water molecules start moving faster and faster. They bounce off each other more and more and move further apart. This means that there's more space between the molecules, meaning that a given volume of water has fewer molecules in it when it's hot than when it's cold. This, of course, means that hot water is less dense than cold water, and so it floats on top. When you go swimming in an ocean or a lake, you can often feel that the surface of the water is warmer, and the water gets cold as it gets deeper. This is because of exactly what we just showed. Warm water is less dense than cold water, so it floats on top. Now, I'm going to try the same experiment, but instead of changing the temperature of the water, I'm going to change the salinity. Salinity is just a measure of how much salt is dissolved in some water. So the water you drink from your tap has very low salinity, while the water in the ocean has a quite high salinity. Now that you know what salinity is, and you know a little bit about density, see if you can make a prediction about whether salty water will float or sink in fresh water.
For this activity, fill 2 glasses a little less than halfway full with fresh water from your tap. Choose 1 glass to be your fresh water and dye it with food coloring. I'm going to use green for fresh. Next, mix at least 3 heaping spoonfuls of salt into the other glass and stir until all the salt is dissolved in the water. Then put a few drops of food coloring into the salty water. I'm going to use red for salty. Similarly to the temperature activity, very slowly pour the fresh water over the salty water, tilting the glass so that it pours down the side until all the water is in one glass. Here we can see that fresh water floats on top of salty water, which means that salty water is more dense.
This makes sense if we think about it, because salty water has more mass than fresh water in the same volume because it has extra salt ions dissolved in it. Together, temperature and salinity are very important in driving water movement in the world's oceans, in something we call thermohaline circulation. Thermo means temperature, and haline means salt. So let's see if we can connect what we've just learned about the density of hot versus cold and salty versus fresh water to the way that the water moves in the oceans. Ocean water at both the North and the South Poles gets really cold, which, as we know, makes it more dense. Some water also freezes into ice at the poles, and when ocean water freezes, only the freshwater part actually freezes into ice, and all the salt is left behind, making the water around the ice even more salty. So given these two factors, do you think that ocean water will rise or sink at the poles? We know that water at the poles is cold and salty, and we know that both of these things make water more dense, so that tells us that water in the oceans will sink really deep at the poles. When this water sinks, new surface water is pulled in from closer to the equator to replace the water that has sunk. And eventually, the new water becomes cold and salty enough to sink as well. Near the equator, the surface water is being pulled away to the north and south to replace the sinking water at the poles, so water has to come up from the deep ocean to replace the surface water that's leaving. This process of sinking water at the poles and rising water near the equator generates the ocean current that we call the global conveyor belt. Now, what do you think would happen to this thermohaline circulation if the poles suddenly got a lot warmer? Well, first of all, warmer water temperatures would make the water less dense and less likely to sink. In addition, warmer temperatures would mean that sea ice would start to melt, releasing a lot of fresh water into the polar oceans. And as we know, fresh water floats. You can probably guess that this would really slow down or eventually stop the global conveyor belt. And in fact, this is already starting to happen because of global climate change. The global conveyor belt is very important in regulating global temperature, moving around nutrients in the ocean, and all sorts of other things. With our rapidly changing climate, polar ice is already melting very fast, and the interruption of the thermohaline circulation currents we talked about is just one thing that could be negatively affected by global increasing temperatures. Experiments similar to the ones we did today, but on a larger scale, are helping scientists to understand the effects of global climate change on circulation currents, and possibly how this might affect our oceans. Thanks for watching! I hope you learned a little bit about density and how density controls thermohaline circulation in the world's oceans. I also hope you had fun building your own density towers.